various equations and get some sort of familiarity with how to draw these graphs. If you've got an equation in x and y, this describes a curve in the plane. Usually, the curve may look something like this. Right? Perhaps less sophisticated than that. An equation in x, y, and z describes a surface in three-dimensional space. Surface may be somewhat complicated. It could look something like this. As can these curves. It might have a hole in it like so and come down here and other part of the surface. There are all sorts of complications that can occur with surfaces. The thing to note here is that if you're trying to sketch a surface in three-dimensional space, your best bet is to try and draw as little as possible. If you try and put into too many details, you find that you don't have much of a picture at all. So an equation of x, y, and z, that's to say some sort of expression in x, y, and z equals to some other expression, right? It's going to describe a surface, just like an equation in x and y, an expression involving x and y equated to some other expression will describe a surface. A specific type of equation, which we've looked at quite a bit, is a function. This is the equation of the form y equals f of x, and it has a specific type of curve associated with it. Namely, for each point x, there's exactly one y over here. We're also going to want to look at functions of x and y. Right? And such a function will have, for each point xy, the equation z equals f of x and y. It will have the surface above the xy plane. As I say, for each point xy, there will be exactly one real number z corresponding to xy, and this will result in a surface that is above or below the points on the xy plane. Now, several of these surfaces we've already looked at, in particular spheres. Right? The sphere of radius r, centered at HKL, let's say, right? As for its equation, x minus h squared plus y minus k squared plus z minus l squared is equal to r squared. Right? So that's one type of surface that we've looked at. And a second one that we've looked at is that of a plane. Right? Plane has an equation of the form ax plus by plus cz plus d equals 0. Right? So these two we've already looked at. We're going to take a look at how to draw the graphs of planes. Spheres are fairly easy. How to draw the graphs of planes and other surfaces, in particular surfaces which are called quadratic surfaces. We're going to begin by looking at graphs of planes. Equations of the form ax plus by plus cz plus d equals 0. Give you a plane for a graph. We're going to consider, first of all, where a, b, c, and d, in particular d, are not equal to 0. So all four of these, if all four of these are not equal to 0. Let's take a look at a specific one here. 3x plus 4y plus 6z plus 12 is equal to 0. Or minus 12 is equal to 0. Better. All right. Better because this is going to be a relatively simple one to draw here. And the way to draw a plane is to, where d is not 0, is to plot the points on the coordinate axes. So we've got x, y, and z. So then in particular, when x and y are both equal to 0, z is equal to 2. So we can plot this point right here, right? Because 6z is equal to 12. When x and z are equal to 0, that's to say along the y-axis, y is equal to 3. So here's a point on the plane. And finally, when y and z are equal to 0, x is equal to 4. So this is a point on the plane. Okay. Having these 3 points where this plane crosses the coordinate axes, one can draw where the plane is located by drawing the triangle connecting the 3 points. Right? And this suggests, of course, exactly where the plane is located. That's to say it continues in this direction here, including this triangle. All right. Let's take a look at another here. Well, what can happen, of course, is that these points can be negative, in which case drawing it is not quite so simple. However, it certainly can be done. I suppose we've got 3x minus 4y minus 6z minus 12 is equal to 0. All right. Then, what have we got here? Well, when x and y are both equal to 0, z is equal to minus 2. So this is a point on the plane. When z and y are equal to 0, x is equal to 4. So here's a point on the plane. And finally, when z and x are equal to 0, then minus 4y is 12, and y is equal to minus 3. So here's the point of the plate. We can now draw this plate as follows. It's back here. Like so. Now, when we did this now, what we've done is we've drawn the intersection of the plane here with the y z plane, the intersection with the x z plane, and the intersection with the x y plane. Each of those is a line. The intersection of a given surface with one of the coordinate planes is called the trace in that plane. So these are the traces in the coordinate planes. And similarly over here. Now from drawing just as little as possible, and that's always a good rule, you can get a reasonable picture of what the graph looks like. So that in both these cases we're dealing with planes. We want to now consider graphs of planes. Ax plus by plus cz plus d So consequently, if you draw the graph of this in the xy plane, any z variable will do. So that in particular, for example, we can plot 2 points of this. When x is equal to 0, y is equal to 5/3. And so here's a point on the graph. 5/3 about there. And when y is equal to 0, x is equal to 5/2. So this is the point on the graph. Right? Since this is the plane, this entire line is on the graph. That's the trace of the x, y plane. Right? Now, any value z that satisfies 2x plus 3y equals 5 will be on this graph. So consequently, we can draw this plane in this direction like so. This rectangle will belong to the plane. Every point that satisfies 2x plus 3y equals 5 is on the plane, and the z value above that can be anything. Right. Similarly here, let's say it's 2x minus 3y equals 5. Okay, let's make this 2x minus 3z equals 5. So there's no y value here, for example. Consequently, if we let x equal 0, we get z is equal to minus 5/3. Minus 5/3 is about there. Right? If we let z equal to 0, and y equal to 0, of course, here, then x is equal to 5/2. So that's this point over here. So this line right here, where this is the x, y, and z axis, is on the graph of this plane. And now any y value, so that 2x minus 3z is equal to 5 is on this plane. And so consequently, this plane looks like this. That's to say, it includes that rectangle. This rectangle doesn't quite look like a rectangle, but this is meant to be a rectangle here. And the plane continues in this fashion like so. Let's look at the case where d is equal to 0. Right? In particular, let's say x plus 2z equals 0. All right? Here we also have y equals to 0. And so if we draw the graph of this, right? If we draw this graph in the graph of this line in the xz plane, right? We've got x is minus 2z. So the graph of this line goes down in this direction here like so. And so consequently, any value y, so that x is minus 2z will satisfy this. And so the plane looks like this. That's to say, it's slanting downward from the y-axis. Let's take a look at another here. X plus 2y plus 3z is equal to 0. Now we have no d term here either. And what does the graph look like? Well, when you've got no d term, the graph always goes through the origin because 0, 0, 0 satisfies this equation. Here, however, now, to draw this particular one here, we're not going to, we've got all three of these terms not being equal to 0, and the best bet perhaps for drawing this is to draw the traces in two of the planes, and these will indicate where the graph is located. So that in particular, when z is equal to 0, we've got x plus 2y is equal to 0, or y is equal to minus a half x. And so consequently, y equals minus a half x is going to look something like this. So this is in the xy plane. When equals to 0, we have x is equals to minus 3z. So in the x is minus 3z, so that in the xz plane, we've got this situation right here. And so consequently, now this is in the backwards direction here. Right? This type of plane is not that easy to draw, but here it is. It contains this triangle right here, which consists of these two lines, namely this one in the xz plane, and this one in the xy plane. Right? So, and this is perhaps the most difficult here, because these two lines are behind the first quadrant. At any rate, this plane goes through the origin, and it goes backwards like this, with this line being in the xy plane, and this line right here being in the xz plane. Okay? So these are basically the pictures involved with drawing the graphs of planes. Of course, if you have got something like x equals 0, this is the yz plane. It has the yz plane for its graph, and similarly, y equals 0 as the xz plane, and z equals 0 as the yz plane for its graph. Right. This and the planes shown in the previous episode here represent all the various types of planes and how to sketch them so that you can tell where they're located. Let's take a look at graphs of ellipsoids. If you've got something in the form ax squared plus by squared plus cz squared is equal to 1, with a, b, and c all greater than 0, then you're going to have what's called an ellipsoid. Unless, of course, if a, b, and c are equal, in which case you're going to have a sphere. This will be centered at the origin, and you can actually deal with these things if they're centered someplace else. We'll take a look at that later. Let's take a look at a specific example. Let's say x squared plus 2y squared plus 3z squared is equal to 1. The best bet for drawing this is to look at the traces of the various planes, so that, in particular, if x is equal to 0, then we're looking at 2y squared plus 3z squared is equal to 1. This is an ellipse. Right? In the yz plane. All right? What does it look like? Well, when y is equal to 0, z is equal to plus or minus the square root of a third. Right? So that if this is 1 unit right here, this is going to be plus or minus the square root of a third, say. Oh, it's perhaps closer to half. Like so. And when z is equal to 0, we're always considering here x equals to 0, then we have got y is equal to plus or minus the square root, 1 over the square root of 2. So 1 over the square root of 2 is about 0.7, and it's perhaps over here and here. And so in the yz plane, what we have is an ellipse. When y is equal to 0, right, the graph is an ellipse. In this is the equation. And if z is also equal to 0, we get x is plus or minus 1. So plus or minus 1 here are also on the graph. And since we've already drawn these 2 points here, we can sketch this ellipse like so. Right? When z is equal to 0, right, we have an ellipse in the xy plane. And we've already plotted these points here in the xy plane, and so all we need to do really is to connect them like so. We've now drawn all 3 traces. Now perhaps I've drawn too much here. That's to say, really this picture is going to look something like this. Right? It's an object somewhat like a sphere, perhaps more like an egg, but each of its cross sections here through the object are ellipses in either the planes parallel to the xy or the yz or the xz plane. You have ellipses here. The 3 traces allow you to see this, and it's clear that anything of this form, ax squared plus by squared plus cz squared is equal to 1, will result in such a graph. So this is the ellipsoid, and in particular ellipsoid with the center of the origin. After the ellipsoid, graphs of cylinders are probably the next easiest to draw. A circular cylinder, of course, is one where you draw a circle and then consider all lines going upward here and downward above the cylinder. So this is meant to extend in all directions. A general cylinder consists of a graph where you take a particular shape, perhaps like so, and usually a shape that's located in a plane, and draw all the lines, not necessarily perpendicular to it, in a given direction. Right? If they're perpendicular, it's sometimes called a right cylinder. So that, for example, all of these points on here will be on the cylinder, and all the cross sections in this direction will have this kind of peanut shaped here going for it. Now, if you've got an equation in x, y, and z, and there's no x, or there's no y, or there's no z, you're frequently dealing with a cylinder. In fact, you will be dealing with a cylinder. For example, x squared is equal to y. Suppose we want the graph of this. Well, there's no z here, huh? So if we draw the graph when z is equal to 0, that's to say the trace in the xy plane, we get what this is y equals x squared, and it's going to look like a parabola, like so. In the xy plane. Now, every point directly above this parabola will also satisfy this equation, because we will have x squared is equal to y squared. So that consequently, the graph of this looks like this. Right? And going downward in this direction also. It's a general cylinder. Okay? There are other possibilities, of course. If we had something like z cubed is equal to x, here we have got no y term. Right? So this is going to be a cylinder. Here we want to draw the graph in the xz plane and then extend it indefinitely in the y direction. So if we looked at x is equal to z cubed, what does this look like? Well, it goes through the origin. And what? X is a function of z, and as z becomes positive, this looks like this. And as z it gets negative, it looks like this. Right? And so that the general graph of this is going to look like so. Perhaps not so easy to visualize, but the graph comes below here like so and follows x is equal to z cubed. It's sort of a sloped cylinder where the cylinder extends in this direction here. Right? So, in summary here, if you've got no z term, or if you've got no y term, or if you've got no x term, right? You end up with a cylinder, and you can sketch that cylinder by sketching the trace in the plane, right, where both of the variables occur. So that, for example, here in the xy plane, and here in the xz plane, and then extending all the lines perpendicular to that plane to form the surface of the to form a picture of the particular surface. I want to take a look at paraboloids now. A paraboloid is called a paraboloid because the majority of the cross-sections of it are parabolas, just like an ellipsoid. All the cross-sections of an ellipsoid are ellipses. Here again, what we're going to want to do is we're going to want to draw the traces, and this will indicate where the graph is located. And sometimes you want to draw traces in planes other than just 3 coordinate planes. But for paraboloids here, of the form we're going to look at, these will suffice. Let's take a look first of all at, let's say, 3x squared minus 2y squared minus z is equal to 0. Right. So if here then are the x, y, and z axes, if we look at what we want here is x squared plus 2y squared minus z is equal to 0. Right? So that if we look at z is equal to 0, the trace in the xy plane, we find that 3x squared plus 2y squared is 0. The only way in which the sum of 2 squares, so 3 times 1 and 2 times the other, can be 0 is if they're both 0. So the trace in the xy plane is the single point here, 0, 0. Right. If we look at x equals 0, right, then what we're dealing with here is z equals 2y squared. So this is a parabola opening upward here, and z is equal to 2y squared, so that consequently, for example, it looks like this. This parabola right here. Okay, if we look at y is equal to 0, we're then considering the x-z plane, and when y is equal to 0, we get z is equal to 3x squared. This is a parabola also opening upward. Looks something like this. Right. So these are the 3 traces, and now it's going to be worthwhile to just consider the basic trace here through z equals equal to a constant, when the constant is greater than 0, and we find that when z is a constant greater than 0, what we have is an ellipse. So this will allow us to draw this, as to say, looks something like this, right? And up here, like this. So like so. And here again, as always, drawing as little as possible produces a picture that you can make sense of. Let's take a look at another here. Let's look at x is equal to 4y squared plus 2z squared. Okay. When x is equal to 0, you get the single point, the origin. So 0, 0, 0 is on this graph, and it's the trace in the yz plane. When y is equal to 0, we've got x is equal to 12, is equal to 2z squared. Right? So x is a function of z here, and we have a parabola that opens upward in this direction like so. This opens toward us. In the x to z plane. When z is equal to 0, we've got x is equal to 4y squared. So in the xy plane, we've got a parabola that looks something like this. And the result is going to be a paraboloid like so. The paraboloid opens outward here with an axis, if you like, which consists of the x-axis. If we look at particular values of x with x greater than 0, we see that we've got an ellipse. So this is properly drawn. And two of the traces are parabolas, thus making this a paraboloid. Okay, so here are two examples of paraboloids. If these open in the backwards direction, they're perhaps a little bit more difficult to draw, but by no means impossible. Now I want to look at what's called a hyperbolic paraboloid. It's basically parabolas in two of the directions, and in the third direction, the cross sections are hyperbolas. And the picture is that of a saddle, or it's usually described as that of a saddle, sometimes even called a saddle or a saddle shape. Let's take a look at a particular example here. Let's say x squared minus 2y squared is equal to 3z. Okay. We want to look at the various traces in the x, y, and z plane. In particular, if we let z equal to 0, we get x squared minus 2y squared is equal to 0. And this is the graph of two lines. That's to say, this factors into x minus the square root of 2y times x plus the square root of 2y is equals to 0. So that the graph has either x equals square root of 2y or x equals minus square root of 2y. Those two lines for the traces in the xy plane. X equals the square root of 2y. Looks something like this. And x equals minus the square root of 2y, something like this. Right? Now this is a little bit misleading, but we'll see what happens here as we continue with this. Let's look at x equals 0. All right? This is the trace in the yz plane, and we get that z is equal to minus 2/3 y squared is the trace when x is equal to 0. So z is this is a parabola. It's opening downward. Z is minus 2/3 y squared. This parabola opens downward like so. In the yz plane. When y is equal to 0, right, we get z is equal to x squared over 3, or 1/3 x squared. So that's a parabola opening upward in the xz plane. Okay, now, what happens here? Well, if you can't tell what this looks like specifically from just these three traces. In fact, it's a bit confusing. However, if we consider various cross-sections of this, let's say fixing x to be a particular number, if x is a particular number here, then we find that what we've got is a parabola, and it's a parabola opening downward. So that each of these parabolas here is sort of hung on this upward parabola here. Right? The resulting shape, I'll sort of sketch it in right now, is like this. And over here, like so. Right? Looks like saddle. All right? Let's see. This should hang on here like so and go over here. This is this part of the saddle, and that's this part of the saddle here. So that in each cross section parallel to the yz plane, we have got a parabola opening downward. In each cross section parallel to the xz plane, if we fix y equals to a particular constant, we've got a parabola opening upward. So here's one of these parabolas here. These other parabolas are going to be parabolas opening upward. Now, if we fix a particular value of z, right, you notice that what we've got, except for z equal to 0, what we've got is a hyperbola. So that this right here, for example, and the other part of it over here, right, are the cross section, like for z of a particular constant, and they form a hyperbola. If z is a positive constant, the hyperbola is up here, like so, and over here. So the cross sections for planes parallels to the xy plane are hyperbolas. The cross sections in the other two directions, however, specifically parallels for planes parallels to the yz plane, or planes parallels to the yz plane, or parallels to the xz plane, those are parabolas. So this is a hyperbolic paraboloid. Its shape is something like a saddle. These lines are on here, and I haven't drawn them real accurately so that they look like as if they're on there, but there's actually a cross on the saddle, right, of two lines. Right? So the cross section here in this xy plane consists of two lines that lie on the saddle. Let's look at another. These are not particularly easy to draw, but with a little practice you can figure out how to do them so that you don't draw too much. Right? Let's look at x squared minus 2y squared is equal to 3z. Oh, let's look at x squared minus z squared is equal to y. Right? Now this is going to be a saddle shape that opens slightly differently. Okay. x, y, and z plane, x, y, and z axes. And now what happens here? When y is equal to 0, we get these two lines again. We have x squared minus z squared is equal to 0. Let's say x minus z times x plus z is equal to 0. So there are two lines in the xz plane, namely x equals z and x equals minus z. When x is equal to 0, we've got y is minus z squared. So y is minus z squared, and that's going to be a parabola opening backwards here, opening backwards in this direction like so. So this is a parabola. Namely, it's y equals minus z squared. When z is equal to 0, we've got x squared is equal to y, or y is equal to x squared, and that's going to be a parabola that opens to the right here, like so. Now, the resulting graph looks like parabolas hung on this particular one here. So if we draw this like this, right, we can get a picture of this saddle. To sit on this saddle, you'd have to lie in this direction here, right? And it's going to look like this. In this direction here, we're going to have hyperbolas. Right? The resulting saddle looks something like this. It's a saddle that can be sat on in this direction here. It's also a saddle that can be sat on in this direction right here. Right. And you can see that if you draw it too much on this, or if you don't draw it fairly accurately, you don't get a good picture of what the thing looks like. So drawing a minimum amount to indicate what the surface looks like is a good idea. And the hyperbolic paraboloids take a little practice, especially if they're not opening upward, so that you've got a saddle that you would normally put a horse underneath. There are two types of objects which are called hyperboloids. One's called a hyperboloid of one sheet, and the other one's called a hyperboloid of two sheets, and that's because the one with one sheet consists of a single surface, and with two sheets has got two parts to it. Let's take a look first of all at examples of hyperboloids of one sheet. Let's suppose we look at, let's say, 4x squared plus y squared minus 5z squared equals 1. With all of these surfaces here, by drawing the traces, you can determine which type of thing you're dealing with. Right? And so in particular here, let's take a look at the graph of this. Let's look at what happens when z is equal to 0. Right? We're then looking at 4x squared plus y squared is equal to 1, right? And that's going to be the graph of an ellipse. In particular, when x is equal to 0, y is plus or minus 1. Those are 2 points on the graph. And when y is equal to 0, x is plus or minus a half. 4x squared will be 1, x squared will be a quarter, x will be plus or minus a half. So here are 2 points on the graph. And this will allow us to sketch this ellipse in here. 5z squared is equal to 1. So when y is equal to 0, and this is the graph of a hyperbola. Right? The hyperbola is in the xz plane. Here are 2 points on it, and we can sketch it like this. Looks something like this in the xz plane. Likewise, when x is equals to 0, we've got y squared minus 5z squared is equal to 1. And this is also going to be a graph of a hyperbola, right? In the yz plane, we've got these 2 points on it, and so we can sketch the graph of this hyperbola like so. The resulting surface is going to look something like this. It looks like a hyperbola in each direction, like so, and an ellipse in each direction parallel to the xy plane. The other 2 directions, the cross sections are hyperbolas. Sort of a spool shape, right? Hyperboloid of 1 sheet. It's got an axis that, in this case, that's equal to the z-axis. And well, all right, this is the graph hyperboloid of 1 sheet. There's 1 surface here. If we fix particular values of z equal to a constant, right? What we're going to end up with here is ellipses. In both other directions, x equal to a or y equal to b, what we've got are hyperbolas for this particular hyperboloid. Let's look at another. We'll say 4x squared minus 3y squared plus z is equal to 1. Okay? Plus z squared is equal to 1. Okay. Right. This is also going to give us a hyperboloid. You can almost see this. Y is 0, we're going to get ellipses. When x is equal to 0, we're going to get hyperbolas. When z is equal to 0, we're also going to get hyperbolas. So, for fixed values of these things, we're going to get hyperbolas in 2 directions, ellipses in the 3rd. Let's take a look at the graph. X direction, y, z. And let's take a look at y equals 0 here. Because then we've got 4x squared plus z squared is equal to 1. And that's going to be an ellipse. Right? And what? When x is equal to 0, z is plus or minus 1. So it's going to be an ellipse like so. When z is equal to 0, x is plus or minus a half. So here are 2 other points on the ellipse. And the ellipse looks something like this. Right. When x is equal to 0, the equation becomes minus 3y squared plus z squared is equal to 1. This is a hyperbola. In the yz plane, we've got these 2 points already graphed, and so we can graph this like so. And down here in the yz plane. When y is equal to 0, we're looking at 4x squared plus, 1z is equal to 0. Right? We're looking at 4x squared minus 3y squared is equal to 1. This again is a hyperbola. Right? Both of these are hyperbolas. And we've got 2 of the points sketched for it, so we can sketch the hyperbola in like something like this. That's a rough sketch, clearly. Right? the resulting solid is going to look like this. Right? That's to say it's going to look like a spool, a hyperbolic spool if you want, which has the y-axis for its axis. Right? In this direction here, we've got a hyperbola. In the YZ plane, we have got a hyperbola. Right? And in cross sections parallel to the XC plane, but that's to say, if we put y equal to a constant, we always get ellipses. So this looks like a spool. It's called a hyperboloid of one sheet, and in this case, its axis is the y-axis. So there are two examples of hyperboloids of one sheet. Now I look at the second type of hyperboloid, the hyperboloid of two sheets. All right. An example of this is as follows. Z squared minus 2y squared minus 3x squared, say, is equal to 4. Right. Let's take a look at the graph. Notice that when z is equal to 0, there's no graph. Because we can't have minus 2y squared minus 3x squared for any x and y adding up to a positive quantity 4. Right? When x is equal to 0, right, we're then looking at z squared minus 2y squared is equal to 4 in the yz plane. This is a hyperbola. And when z is equal to 0, there's no point on the graph. When y is equal to 0, z is plus or minus 2. So plus or minus 2 for the z. Right. And this is a hyperbola, and it opens like this in the yz plane. When y is equal to 0, right, we're looking at then z squared minus 3x squared is equal to 4. Again, here, when z is 0, there's no x value, but when x is equal to 0, z is plus or minus 2. We've already plotted that point. And so what we've got here is a hyperbola opening upward in this direction. In the XZ plane. So the resulting graph of this is going to look like so. And down here, it's going to look like this. Where the cross sections here are hyperbolas. And now if we pick a particular z equals to, if we take a particular z equals to a constant, if the constant is large enough, then we're going to get a negative number here, and we're going to get something that looks like 2y squared plus 3x squared is equal to a constant, and so that these are going to be ellipses for a large c, the large values of c. When z is equal to c, the cross section in that particular plane is going to be an ellipse. Let's take a look at another. X squared minus 4y squared minus z squared is equal to 9. Okay, let's look at the graph of this. x is equal to 0, there's no graph. Because we can't have, again, minus 4y squared minus z squared adding up to a positive quantity 9. So when x is equal to 0, there's no graph here in the yz plane. Let's take a look at when z is equal to 0. Right? When z is equal to 0, we're looking at x squared minus 4y squared is equal to 9. Well, if we also look at y equals 0, we get x is plus or minus 3. So here are 2 points on the graph. Minus 3 and at 3. Right? And the graph is a hyperbola, and it's in the xy plane and opens like this. And back here like this. When what do we have left here? When y is equal to 0, right, then we're then looking at x squared minus z squared is equal to 9. Right? If x is also equal to 0, there's no value z, but if z is equal to 0, the point x is plus or minus 3, we've already plotted that right here. What we end up with here is a hyperbola that opens in the xz plane like so, and over here like this. Right? The resulting graph then is going to look like this. Right? It's got hyperbolas for cross sections, and if we let x be large enough, or if we let a be large enough, and look at x equals a, we're going to get ellipses. When x is large enough, in particular where x is larger than 3, then this is going to give us 4y squared plus z squared is equal to a positive number here. We're going to get ellipses. So that this resulting graph has got 2 parts to it, 2 sheets if you want, and it's a hyperboloid of 2 sheets. So these hyperboloids look pretty much like this. Of course, third possibility that it opens it, or it has an axis as the y-axis. And of course, there are also possibilities of translating this or moving it around in space. But for this type of equation, this type, right, by plotting the traces, you can see what you're dealing with. And a hyperboloid of 2 sheets is the name for this particular surface. Now comes to the last of these quadratic surfaces here that we're going to consider, which are the cones. And again, here you can see what you're dealing with by looking at the traces. We have something like x squared minus y squared minus 4z squared is equal to 0. Right? This is going to be a cone. Let's take a look at the traces in the graph. What happens here? If we let x equal 0, we get a single point, namely the origin. So the origin is on this graph, and it's going to be the only point on the yz plane. Right? If we let y equal to 0, we get x squared minus 4z squared is equal to 0. And we can factor this into x minus 2z times x plus 2z is equal to 0. And consequently, the graph is the graph of 2 lines. X equals 2z and x equals minus 2z. So x equals 2z looks something like this, and x equals minus 2z like this. We look at z equals 0, got x squared minus y squared is equal to 0, and I can factor that into x minus y times x plus y is equal to 0. And so we get two possibilities. X minus y is 0, that's to say x equals y, or x plus y is 0, x equals minus y. So we've got these two lines here then for the trace. X equals y, or y equals x, and y equals minus x. The resulting surface is going to look like this. And back here, like this. Right. Let's see here. This goes to here. This is x equals y, and this is x equals, so these two are over here like this. And this one is up here. And this one's down here. So it's a cone. In the cross sections, if we fix a particular value of x, x equals a, we find that we've got what we should have here is an ellipse. For particular values of a, yes, we've got what? A squared is equal to y squared plus 4z squared. So these are ellipses in the cross sections here for particular x equals to a. Let's take a look at another. Z squared, say, minus 3x squared minus 5y squared is equal to 0. Now, you can sort of see the form here. You've got two negatives and a positive, or vice versa, and a 0 here for a constant term. However, it's not really worthwhile to memorize all these various forms. Your best bet is to just take a look at what you're dealing with and draw the particular picture by getting at the traces. So, in particular here, when we have z equals 0, we get only the origin. So the origin 0, 0, 0 is on this graph. This point right here is on the graph. That's the only point in the yz plane. When x is equal to 0, we've got z squared minus 5y squared is 0, or z minus square root of 5y times z plus the square root of 5y is equal to 0. Right? These are two lines. Z is the square root of 5y. So z is the square root of 5y, and z is minus the square root of 5y. These are two lines in the yz plane. Right? When y is equal to 0, we have z squared minus 3x squared is 0. So the trace is going to be z minus the square root of 3x times z plus the square root of 3x is equal to 0. Again, two lines in the xy plane. They look something like this. And the resulting graph is going to look like this. Likewise down here, in the xy plane, the resulting graph is going to look something like this. Right. The result is a cone with the z-axis as axis. And the cross sections here, if we pick a particular z equal to a constant, right, we're going to get ellipses. When z is equal to constant, we're going to get 3x squared plus 5y squared is equals to the constant squared. cones here, one opening in the direction of the x-axis, the other one in the direction of the z-axis. I want to take a look now at what happens if one of these things is translated. These quadratic surfaces have equations that look like ax squared plus by squared plus cz squared plus dx plus ey plus fz plus g equals 0. Right? Your ellipsoid, sphere, planes, hyperboloids, paraboloids, hyperbolic, paraboloid, the cones all have this form here. Right? And the existence of these terms here usually indicates that if you've got a z-squared term along with a z term, it indicates that you've got a different center for the thing. Right? Likewise with a y squared and a y and an x squared and an x. And the way to graph these is to consider things as it translates to a new center by completing the square of any term that we've got the term and also like x squared and also the x term. Let's take a look at an example. Say 2x squared minus 3y squared plus 4x plus 5y minus 6z plus 7 equals 0. Okay? Now here we don't have a z-squared term. Let's collect the x terms together here. So we're going to have 2 times x squared plus 2x plus minus 3 here times y squared. And we want now the y-th term. If we put this inside the parentheses here, it's going to be minus 5/3 y. All right. And what? Minus 6z plus 7. Let's leave that for the moment equals 0. Okay. Completing the square here, we would want to add 1, which means that we've added 2 actually to the right-hand side here. It's not fair to do that without adding 2 to the left-hand side. With this square here, we divide this by 2. We get 5/6 squared. We get 25/36. Right? What have we done here? We've added 25/12. Or we subtracted 25/12 from this side. We need to subtract 25/12 from this side here. Right? So that all together here, what we're going to get is 2 times x plus 1 squared minus 3 times y minus 5/6 quantity squared is equals to minus 6z plus 7. What have we got over here? We've got 2, which is 24/12 minus 25/12. So this is minus a 12th. So we've got plus 7. And if we add a 12th to both sides, we're going to have 7 and 1/12. Right? We can write this then as minus 6 times z. 7 and a 12th is 85/12. So we've got minus 85 over 12 here. We want to multiply this by 6, however, so 72. So that 6 times 72 here will give us 85/12. So here then is the equation, right? And if we let x bar be x plus 1, y bar be equal to y minus 5/6, and z bar be equal to z minus 8570 seconds, then this equation becomes 2x bar squared minus 3y bar squared minus 6z bar is equal to 6z bar. If we wish to graph this, we want to find out where the center of the x bar, y bar, and z bar coordinate systems are. And let's take a look at that. X bar is equal to 0 when x is minus 1. So at x equals minus 1, we've got the center of this system here. When x is equal to minus 1, we've got the center of the system. Right? So x equals minus 1. Y bar is equal to 0 when y is equal to 5/6. So y equals 5/6. And z bar is equal to 0 when z is equal to 8570 seconds. So that's a little more than 1. So up here, the center of this coordinate system then is located over here. We then have a new coordinate system like so, with this as the center. And now what we wish to do is we wish to draw the graph of this located at this center. Right? Well, what does this look like? Let's draw it over here. When z is equal to 0, we get two lines. So we get the two lines. When z bar is equal to 0, we get two lines here. What was this? This was the center. The center is at minus 1, 5/6, 85/12, 8570 seconds. Right? Okay. When z is equal to 0, we get two lines in the xy plane, or x bar, y bar plane, and they look like this. Right? When y is equal to 0, we've got z is equal to 1/3 x squared. So z bar is equal to 1/3 x bar squared. This is when y bar is equal to 0. Right? So this is going to be a parabola opening upward in the x bar z bar plane. Right? When x is equal to 0, we've got z bar is equal to minus 3y squared, minus a half y squared. So z bar is minus a half y bar squared when x bar is equal to 0. Right? That's parabola opening downward. Right? This resulting shape is a hyperbolic parabola and looks something like this here. We've got parabolas opening downward in this direction. It's a saddle shape over here like so. So what we want to do to draw the graph of this is to relocate this saddle shape over here. And here perhaps too much has been drawn to see this picture clearly, but what we have then is a saddle with this new center at this point right here. Okay, a saddle that looks something like this. Z bar, x bar, or y bar, and x bar system. Okay. So when you have something that looks like this, you can complete the squares of any terms that have got a square and a constant term, and find a new center for the graph, and it will be one of these surfaces that we've been looking at, which are called quadratic surfaces. surfaces now which are generated by revolving a curve about a line. In particular, we'll just look at the simplest here, although knowing how to do this will allow you to do more complicated ones. Let's suppose that we've got z as a function of y. Something that looks like this, perhaps, or this is the x-axis, the y-axis, z-axis, and this is drawn out in the yz plane. And suppose we wish to rotate this about the y-axis, right, forming a surface of revolution like so. Right. We want to know what the equation of such a surface might be. And for that purpose, let's consider a general point x, y, z on the surface and determine what it takes for x, y, z to be on the surface. Well, if we draw this down here, and this is the point x, y, 0. And if we draw this over here to the y-axis, this third point here, of course, is going to be 0, y, 0. This point here. And in order for a point x, y, z to be on this curve, what must happen is that this distance right here must be equal to the value of the function, so that we get a circle over here. Right? That's to say, what we must have is that this point right here, x, y, z, its distance to the point 0, y, 0 is square root x squared plus z squared. Right? This must be equal to the value of the function up here, namely f of y. Or if you like, x squared plus z squared is f of y squared. Right? So if you've got z is a function of y, and you wish to find the equation for the surface of revolution gotten by revolving this about the y-axis, right? You can get it like so. It's not worthwhile, particularly to memorize these formulas. You can determine what is needed for a particular point x, y, z to satisfy an equation, and then write the equation to satisfy a particular description, and then write the equation for that. Similarly here, let's take a look at this picture. Let's suppose that we've got z as a function of x. Right? And so we've got z as a function of x over here. Perhaps like so in the xz plane. And suppose we wish to revolve this about the x-axis, producing something that looks something like this. Well, what does it take? What does it take for a point, let's say here, to get on this surface? Well, this is the point x, y, z. And this point down here is the point, what? Where z is 0, so it's x, y, 0. And this point over here is the point x, 0, 0. And for this point to get on there, what we need is that this distance right here, namely the square root from this point to this point, the square root of y squared plus z squared, must be the same as the value of the function here at the particular point x. So this must be equal to f of x, right? Or y squared plus z squared is f of x squared, gives you the equation of this solid of revolution. Now we've looked at the solid here at this point of one type here, namely where you've got a function and you wish to revolve it around the axis of the independent variable. In this case, z is a function of y. We're going to revolve around this axis. Clearly, we could revolve it around. We could revolve this around the z-axis, and we'll look at this next. We could also revolve this around any line whatsoever, and by simply writing what it takes for a point to get on the surface, let's take a look at another solid revolution here. Let's take C is f of y, like so here, and imagine rotating it about the z-axis. Produce something that looks perhaps like this. Well, not a very good drawing, perhaps more like this here. Okay, so x and y. And now, what does it take for a point to get on the surface? Say this point right over here, what does it take to get on the surface? Well, this is the point x, y, z. Right? Then, this is the point x, y, 0. Right? And if we rotate this over here like this, so that this is the same distance, right? We should have that this height, z, right, is the value of the function over here. So z must be equals to the function at the square root of x squared plus y squared. Right? Slightly different principle here, but basically the same idea. Take a point x, y, z, you ask what does it take for it to get on this surface, and this is what must happen. F of x squared plus y squared square root must be equals to z. Okay, let's take a look at a specific example, or a semi-specific example. Let's suppose we want to form a donut shape, which is called torus. By taking a circle of radius little r, located here in the y-z plane, and rotating it about the y-axis to produce something that looks like perhaps this. All right. And this radius right here to the center is going to be capital R. So capital R is this distance right here. Okay, well, here's a point on the circle in the YZ plane, and it must, that's to say, this is the point 0YZ, and it must satisfy what? Y squared, well, all right, this point right here is the point 0, 0R. Right. So this point must satisfy y squared. The distance from here to here must be r. So y squared plus z minus capital R quantity squared must be equals to little r squared. So this point satisfies this. Or if you want here, if we take a look at r squared minus y squared, this is equals to z minus capital R squared. So the square root of this is z minus capital R plus or minus the square root of it is z minus capital R. So z must be equals to capital R plus or minus the square root of little r squared minus y squared for this point to get on here. Now how about general point over here? Well, recall that if we consider this as two functions, for example, the upper half of the circle and the lower half of the circle being the plus and minus part of the function here, then to revolve this around the y-axis, a point gets on here if this distance right here, right, this is the point, general point x, y, z, and this consequently right here is the point 0, y, z. We must have this distance, which is the square root of x squared minus x squared plus 0, y, 0. Right? The square root of x squared plus z squared must be equal to the value of on the function. Right? So this must be equals to this distance, square root x squared minus z squared, must be equals to r plus or minus the square root r squared minus y squared. So that's here, and you can of course simplify this by squaring it a couple of times, is the equation for this particular torus. Okay, so the general principle is to determine what it takes for a point x, y, z to belong to the surface. And there are some variations on this. We don't want to study functions in great detail, but for the moment, let's just consider when you've got a case of a function and you want to graph the resulting surface. And the case that is usually considered is where z is a function of x and y. Right? What this means then is that for each point x, y, right, there's one value z. This is going to result in a surface that is located above the xy plane. And so if you've got an equation in x, y, and z, and you can solve it for z, you can then start graphing this by plotting points if you want, by first solving it for z, and then looking at what happens at various values of x and y. There are a couple of other possibilities, all right? Here's z as a function of x and y. You can also have y as a function of x and z. Say y is g of x and z. In this case here, given a particular x value and a z value, you would have one specific y value. You'd end up with a surface that has for each x, z, one y value. The surface consequently would lie over or perhaps above it below, but nonetheless each point xz, there would be a point here that would lie above or below the xz plane in the y direction. And of course the third possibility is that x is a function of y and z, in which case for each particular pair yz, there would be a unique x. And so if this is x, y, and z, the graph would lie somewhere out here. An example that we've already looked at of this form right here is, let's say z is equals to x squared plus y squared. For each x and y, there's exactly one z. And in particular, if we take a look at a point xy here, the z is positive. If we look at the traces here, for example, when y is equals to 0, we get a parabola in the x z plane. When x is equal to 0, we get a parabola in the yz plane, and the resulting surface is going to look like this. Right. So that above this particular point xy, there's going to be exactly one point here on the surface. So here's an example of a surface that we've looked at already that is where z is a function of x and y. These other surfaces, other types of surfaces could be drawn keeping the fact that you're dealing with a function in mind. procedure, we're going to want to consider two additional coordinate systems, and the first of these is called cylindrical coordinates. And instead of writing things in terms of x, y, and z, we want to correspond to a point here which would normally correspond x, y, and z. We want to correspond with triple r, theta, and z. Right? So that if this is the z distance here, we want this to be the angle theta between the x and y axis, and this to be the distance r. We want it to correspond then with x, y, z, the triple r, theta, z. And this simply consists of putting polar coordinates on the x, y plane. And so consequently, what have we got here? We've got, if we know x, y, and z, x squared plus y squared, square root is going to be equal to r. Theta is going to be the angle whose tangent is y over x. So if we know x, y, and z, we can get theta. And of course, z is going to be equal to z. Right? So this allows you to get r, theta, and z given x, y, and z. On the other hand, if we've got r, theta, and z, x is r cosine theta, just as in polar coordinates. Y is r sine theta. And z, of course, is z. Now, cylindrical coordinates are most useful for drawing things that tend to be cylindrical. In particular, for example, if we looked at r is equal to a constant, the graph of that would be this cylinder here of constant radius r. If we looked at something like r times z equals 4, we wanted the graph of it, right? Rz equals 4 is going to look like this. Okay, if we look at this in the yz plane, for example, or the xz plane, it's going to look like this, right? Actually, it's going to be a hyperbola, and the resulting graph of this is going to look like what you'd get if you rotated this around the z-axis. And there's a bottom part to this also that looks like so. Right. So that for dealing with rotations, cylindrical coordinates are frequently more useful. And this allows you to change from x, y, z, rectangular coordinates, to cylindrical. And the second one here allows you to change back. If you've got r, theta, and z, you can get x, y, and z in this fashion right here. Type of coordinate system, which is called spherical coordinates eventually here. And they look like this. Instead of x, y, and z here, right, if we've got a point, we're going to want to know theta here, this angle, the distance to the point rho, and this angle over here, which is designated by phi, the angle with the z-axis. So this is the point x, y, z. Right? Sometimes it's going to be convenient to switch this over into these spherical coordinates. What do we have here? Well, we have x squared plus y squared plus z squared. Square root will give us rho. Right? It's also permissible permissible to have a minus rho here, which would give you the point down here like so. But theta is as before here, the angle whose tangent is y over x. And now phi. Well, if we've got x, y, and z, we want to find phi. There are several ways to go about this here. And z, for example, over rho right? The z height here over rho is going to be the cosine of phi. So phi, for example, can be computed as the cosine inverse of this quantity, yeah? Right. Okay, so given x, y, and z, you can find rho, theta, and phi. Let's suppose we've got rho, theta, and phi. Right? We want to find x, y, and z, given a rho, theta, and phi. And z, perhaps simplest here, is equals to rho cosine phi, yeah? That'll give us the z value here. Right. Rho sine phi will give us r. So that consequently, since this is r, that's r here as in cylindrical coordinates, then x is going to be rho sine phi cosine theta, and y is going to be rho sine phi sine theta. Now, cylindrical coordinates are more useful when you're dealing with something that is like a cylinder. That's to say, for each vector emanating from the origin here, there's a point on the surface. In particular, for example, if we look at the graph of rho equals 3, this is the sphere of radius 3. Yeah? Right? If rho is a function of phi and theta, then you're going to be dealing with something where for each direction here, away from the origin, there's a point on the surface. So this is the graph of rho equals 3, a sphere. All right. And here is then how to change from spherical coordinates to rectangular, and how to change from rectangular to spherical.